So let's get started. So we're going to start a new topic today. So on gradient descent. So this is probably one of the most fundamental kind of like one of the most fundamental algorithmic building blocks of data analysis. But before we had this class in the curriculum, we found it was not really being taught. And so this kind of underlies how what most of the computational resources are usually spent on. So within most of machine learning or data mining or kind of most sorts of data analysis, where you're actually trying to build models to make predictions. So we'll see, as we've seen so far in like the case of linear regression, we basically saw a different way to build the model so far. But in not all cases are we so lucky that there's this nice kind of closed form solution for like this alpha model here. So usually what is resorted to is this idea of gradient descent. Okay, so before I jump into the lecture a little bit, let's just quickly look at the schedule. So it says homework 3 is supposed to be out by now. This was posted last week Friday already, so that's posted. The first 2 questions you should be able to get started on. A lot of this assignment will actually be in Python. The third question we'll see most of what you need in the lecture today, but we'll actually go through the actual algorithm in class on Monday, and some sample Python code, and so that will really be the foundation of that question. And then as we discussed, I decided after voting and a close vote, and hopefully everything was there weren't any discrepancies in the vote counting, but so I've moved back quiz 5 and 6 by a week. So they're still going to be on a Monday, but they're both shifted back a week. This will, with this extra break in the day for election day, the day after election day, when we won't have class, now the quizzes will actually fit a bit better with the material we're planning to cover. And then we'll have some quiz on the classification part as well. So I think this fits the schedule better. And then you'll get more, the quizzes you can think of as kind of practice for the final on the different sections. And so then you'll get kind of pretty much, because the classification section will have part of a quiz now, you'll see basically the practice for the final on those questions as well. And you'll have a little bit more break in a few weeks. Well, actually, because we'll push back the quizzes also. So hopefully, I think this is the right way to adjust the schedule. Okay. So let's get on with the lecture. Okay. So the main concept here is going to be talking about these functions, right? And if we remember with linear regression, we had this data where we have basically an x coordinate, which is in RD, and we had this y coordinate in the real numbers. Okay, and so we had drawn pictures with this kind of with the coordinates x and y, these data points. We're going to draw something different now. We're going to draw a function, and instead of x, we're going to think of now of alpha as being on the x-axis. Okay, so it's still like the x-axis, but now this is alpha. This is the space of the models. So this is going to be the space of models, and we're going to think of some sort of function Okay, and there's this function which goes from basically from any point. This is some value of alpha that is a model, and it's going to go up to this function for every thing on the x-axis, every value alpha, there is a function value, right? This is now going to be the function value. This is going to be f at alpha, where this is some function f. This function goes from rd to r, okay? Right, so we're going to, so the premise of the section is going to be kind of gradient descent is looking at things like this, right? And this is generally going to be a cost function. So e.g. the sum of squared errors, okay? In the past, we've been thinking of similar setup where the x-axis was actually the x value. Now's the function value, okay? And typically the functions look like a dot product with x or something kind of that form. So they're going to be roughly the same dimensions as x also, right? So these are also going to be these d-dimensional. So the domain of the function will still be d-dimensional, okay? And so the goal is the minimum. So it's going to be right here. So this, you can think of this as two ways. You could think of this point down here as alpha star. It's the function, the argmin, or you can think of this minimum value. This would be min of f, and this point would be the arg min of f, right? And we can think of this as alpha in rd of f of alpha. So alpha star, and this as being the min value of f of alpha for alpha in rd, right? So that's the minimum value of the function, okay? Right? So this is the kind of the generic setup. We should think of this function f, right? The most common form of this function f of alpha is going to be the sum of the squared errors of x, y, the model of alpha, right? So this was equal to, just to try and make this concrete, 1 to n. There are n data points, where it's going to be yi minus the dot between xi and alpha squared. Okay, so this is an example. Okay, and this is basically what the linear regression function looks like, but it could be other functions like this. Okay, so instead of thinking of this as a function of the data, right, we thought of this model term here, right? We could use this as a function m alpha of xi. We thought of that as a function of the data, but now we're thinking of a function of the model, and we want to find the model which minimizes the cost. And we say cost is that on the training data that we're using, we're trying to get the best prediction of the labeled values. Okay, so this is kind of when we're talking about functions, this is what you should have in your mind. We'll talk about other functions as well, other than this sum of squared costs, but we'll also see why this one is going to be particularly kind of has nice properties. Okay, so that's what we'll kind of talk about over the next few lectures. So yeah, so okay. Sure. And so I should say, just so it's clear, a function from, if you look at this expression here, this is saying that f is a function with a domain of Rd and a range of R. So its domain is the input. It takes a value from Rd, okay, and this could be an alpha vector, a vector which is, could be here, alpha is equal to alpha 1, alpha 2, up to alpha d, right? And it outputs a single scalar value, right? For every value alpha, there's exactly one for every vector alpha, there's exactly one scalar value that's output, right? Okay. So it can't do something, you could not have a function that looked like this, right? Because now for one value alpha, for one vector alpha, there are two possible function values. You can't have something like that. Okay. Good. So this is the idea of a function. These are kind of easy to imagine in low-dimensional spaces, especially in one dimension. Probably in your calculus classes, you probably at least talked about them in one dimension, kind of thinking about them this way, and maybe even two, with a few dimensions. We're going to really need to think about ways to interpret them that are consistent with high dimensions, when the domain is very high dimensional. So we'll talk about definitions, but through linear algebra, they're going to kind of generalize naturally at high dimensions. And that's going to be important because we're going to want to potential to build complex models that have d parameters. And to do this, you need high dimension case here. So, okay. So the next part of the lecture is going to be a bunch of definitions kind of needed to formalize this. So we're going to talk about some properties, and so definitions of functions. But I'm going to take a more of a geometric view of this and not a calculus first view of it. You maybe have seen a calculus first view of this before. We're gonna need calculus where gradient descents are based on gradients, which are derivatives. But I'm going to try and introduce this as a geometric view, so you have that to go along with the very natural kind of calculus view of it. So the first thing we need in order to do this is the idea of a local neighborhood. Okay, so for some alpha in Rd, okay, and the local neighbor is going to be a subset of Rd around alpha, and there are a bunch of ways you can define it. We're going to define it with a say a Euclidean ball. So we're going to say a ball of radius alpha around Rd is going to be the set, curly brackets mean it's a set of all, let's say points P in Rd, such that the distance, the Euclidean distance between alpha and P is less or equal to R. In this case, it's a closed ball, so it includes equal to R. Okay, so if I'm in Rd, in this case it's R2, I'm going to have one point here, alpha. I'm going to draw some radius R, and the Euclidean ball is just going to, we can draw a circle of radius R, and Euclidean ball is going to be all of the points inside this, inside and including the circle. Okay, so in a local neighborhood can be defined as as a sum ball BR of alpha for a sufficiently small value r. Okay, so I want to think of this as this. I want to define some local properties of the functions, and these will be important because we're going to talk about special points, the minimum and the maximum and these saddle points. In order to think about them, we need to think, well, they're talking about what happens very locally. And how local is local, how close is close? Well, when I'm defining them, I don't totally know. And I'm saying there's some small enough radius where things look kind of, they're consistent inside this ball. So I can make this r as small as I need to make it. I can make this ball small enough so that things look kind of consistent inside the ball. Okay. For sufficiently small r, I should say that r is a scalar value. It's greater than 0. It can't be 0 or it can't be negative. That wouldn't make sense. Okay. Okay, so then kind of why we want to do this is because we want to define a local minimum. Okay, so this is of f. Okay, and this is a point alpha in RD. So for all P in some local neighborhood, that f of P is going to be greater or equal to f of alpha. Okay, so we can think of some function in just d is equal one-dimensional here. And if you have a point alpha and I take any local neighborhood here, all of these function values are going to be larger. I can think of drawing some line that goes through here, and that goes through that value at alpha. And the blue function, at least within that neighborhood, that radius r neighborhood never dips below that red line. Okay, so this is a local minimum. Okay, and you can define a local maximum. Okay, where this is where it's the same, except f of p is going to be less than or equal to f of alpha. Okay, and then we also say that these are strict if instead it's going to be f of p greater or equal to f of alpha for p not equal to alpha, and f of p less than f of alpha for p not equal to alpha, right? So if I say it's a strict local minimum, that means that everything is greater than, has a function value greater than alpha, not just greater or equal than. And I have to not exclude alpha, of course. Alpha is inside the local neighborhood, but everything other than alpha itself. Okay. Okay, and so these minimum are kind of the best sort of minimum, as we say that a global minimum, and we can say maximum also, is the alpha in RD. So f of p is greater or equal than f of alpha for all p in RD, right? So if this holds for all of RD, and similarly, f of p is less or equal to f of alpha for all P and RD, right? So I don't have the local neighborhood restriction anymore. Okay, so for some, so if I have a function like this, okay, so this is a local min, and this one is a local minimum, and it's also a global minimum. Okay. We can also think of having should think of a function that looks like this. Okay, if I have a function that looks like here, what's happening is that the function is a constant down at the bottom here. All right, so this might be a global minimum. But what's different about this one is that there's a bunch of things in any sort of neighborhood I define that have the same function value. So this is not a strict global minimum, where this one is strict, because all the function values except for this alpha right here are going to be greater than that. Where you can have some cases where you're going to have a bunch of function values which are exactly the same. You could also have the case where you have like this, where you're going to have two values which are going to have the same minimum here. Okay, so that again, these are both these are both global minimum, I guess, in this case, but they're not so a unique global minimum. They're both local minimum, and they're strict. Okay, but they're not yeah, but they're both global minimum, but they're not strict global minimum, but they're strict local minimum. Okay, so these are strict local minimum, not strict global minimum. Okay, so these are kind of some interesting cases. And might surprise you, but we will actually see cases that look kind of like both of these. They'll occur in higher dimensions. So you can actually construct, so these might occur in low dimensions as well. What is strict locally? Okay, so the idea is that this one, if I look in a local neighborhood, all the function values are above those red points, the minimum. But if I look in a global neighborhood, I look at all of RD, so this one, the one in the bottom right corner is strict local minimum, but not a strict global minimum, because there's another function, there's another alpha. If this is alpha, there's another alpha prime that's not in the local neighborhood, but it has the same function value. Okay, great. Yeah. Good. So when we deal with, so the top one where there are a bunch of things that have the same value, if you're trying to find the median or the L1 minimum instead of the sum of distances instead of the sum of squared distances, you'll get functions that look like that. Actually, if you're trying to find an underdetermined linear regression function, it looks like this top picture in high dimensions. In k-means clustering, we'll talk about, you can get examples that look like this case on the bottom as well. And with symmetry, these actually happen a lot within, say, like with inside deep learning, where you'll get many equally good local or global minimum, and you actually don't know if they're local or global minimum in that case. Okay, so these things actually occur. That's why it's worth talking about them and having a language to try and discuss these things. Okay. Okay, so I'm going to try and loosely define a continuous function. Okay, so we're going to talk about differentiable functions later, and continuous is a weaker notion than so differentiable. So f if for any alpha in RD there exists a there exists a sufficiently small value, delta greater than 0. So there exists some radius r delta that depends on delta. So p in some local neighborhood that depends on this r delta of alpha has that f of alpha minus f of p is less than or equal to delta. Okay, so there's kind of, the idea is that if you have some function value and I can basically draw it without lifting up my pen, and it's still a function that it's, and I don't have any strictly vertical lines, then this one is going to be so continuous, whereas a function value like this, so this is not so continuous. And that's because there exists this jump in function values right here. So if I were to pick my alpha right here, I move to the left, I move just the left of it, I can't draw a local neighborhood small enough so that the function value doesn't have a big jump someplace. Okay. So we'll be talking about these, we'll almost always be talking about these continuous functions. So, okay, so if you remember when I talked about the eigenvalues and eigenvectors yesterday, I said, there's a lot of complex stuff, actually, like very literally complex stuff going on there. But, I said, only worry about these positive semi-definite matrices because these come from data and then things are much nicer. That's what I'm doing here with these functions. I'm saying, look, the idea of functional analysis is this huge, vast space, and we don't care about most of it. So we're going to focus on continuous functions. Okay, this is what will make sense. We're going to model a cost function. As I slightly change the model, I want my cost to vary continuously. I don't want it to have these jumps. Now, that sometimes happens, right? In some data analysis, you'll do some things where the model changes kind of, as I change it a little bit, it's going to have these big jumps, and these are going to be much harder to work with under gradient descent type operations. But they occur in some other sort of things, and you need some more discrete optimization. And we'll talk about these algorithms, say, in the context of k-means clustering. This sort of stuff might actually happen. So okay. Okay, we're getting a little bit closer through here, and then this lecture is going to be a bunch of these definitions, kind of just how it's going to go, but they'll give us the language to talk about kind of the cool things you'll want to know about gradient descent. Okay. Okay, so the next kind of notion we need to talk about is going to be is going to be a saddle point. Okay, and this is where I'm not going to be able to draw really these one-dimensional functions anymore. So this is a point in RD. You can define a saddle point in a different way for these when D is equal to 1, but these are usually called an inflection point instead, or something kind of like that. That's similar, but that's not really what we're going to want for talking about high dimensions. And there's a way to define this with gradients, and we can maybe mention that later once I define gradients. Okay, but okay, it's going to be a point in RD. So in this local neighborhood of alpha, there are some p with the function value of p is going to be greater than f of alpha, and some p prime with the function value of p prime is going to be less of f of alpha. Okay, so far this isn't actually very interesting, but it's going to have another condition. But so in fact, I'm going to call this P1 and P2. These are, I think of 2 points, and this will be P1 prime and P2 prime, but there is no path from, say, P1 to P2 without passing through alpha or some p prime such that f of p prime is less than f of alpha. Okay, so this seems kind of strange if you haven't thought about it this way before. Let me try and draw a picture up here, okay, of the saddle point. And so now it helps to draw the local neighborhood, say in R2 here, right? So this is, in general, RD. Let's think of this as R2. And so I've got alpha here. Okay, so what's going on? I'm going to have some point, call this point P1, call this point P2, call this point P1 prime, this point P2 prime. And I'm going to be able to kind of draw these regions here. And then all of the points near P1 and P2, these are all going to have f of p is going to be, let's see, this is greater than f of alpha. And then I'm also going to draw these regions around P1 prime and P2 prime. And these are going to have f of p prime are going to be less than f of alpha. Okay, so what you should think of this like a saddle. So like a horse's saddle. We're in the West. Hopefully you guys know what a horse saddle is. And where the rider sits, they put their legs going down on either side. But in front of them, the horse's kind of front and the rump of the horse kind of go up on either side, right? So it's going to look like it's going to go down here and it's going to go up, right? So maybe this is a dashed, right? So the function value is going to try and go up on 2 sides and go down on 2 sides, right? So in the green regions, it's going up away from alpha, and in the pink regions, it's going down. Okay, so there's a hand raise. Go ahead.
So when I've heard of saddle points being talked about before, usually the example I see is like an x cubed algorithm where it rises, the derivative goes to 0 and then continues to rise, and the point in the center is a saddle point. Would that be a saddle point like what you're describing?
It goes to 0 and then it continues to rise. So yeah, so an x cubed function, you're thinking instead of like an inflection point, right, where this is f of x equals x squared, x cubed. Okay, so this is where for a point alpha, it's going up in one direction, it's going down in the other direction. Okay, but this is only a one-dimensional function. I would refer this as like an inflection point instead. The derivative, as we'll define, is 0 at this point. Okay, and so sometimes called a saddle point, right? And so kind of the issue with saddle points or with this point right here is that the derivative is going to be 0, and I haven't defined derivative yet because I'm trying to delay the calculus a bit, but the derivative is 0, which means we won't know what direction to go down. And that's going to be the same at this saddle point here as well, the one I've drawn in R2. Okay, but the difference here with this one is that there is a right direction. In the case of the inflection point, there is one direction that if I tried something at random, I would start moving and then I could get out of it and I'd know I go in the right direction. With the saddle point, it's more complicated in that think of this as like the Continental Divide. Okay, so I'm walking along maybe the Rocky Mountain Trail or something. I don't know if that's right in the Continental Divide, but it's kind of the ridge of the mountains. As I go through a pass on the mountains in between two peaks, right? Think of, I can go up either ridge or I can go down either side of the mountain. And depending on which side down I go, I may go to a different local minimum. I might go out the Mississippi River into the Atlantic, or I might go out the Colorado River into, or the Snake River into like the Pacific. Okay, and so I don't know which is the right direction to go, and depending on, if you get stuck in a saddle point, you can say if you just look at the gradient, you can say the gradient is 0. The thing is, you're very unlikely to actually be in a continuous function on the saddle point. It's a point of measure 0, so you're unlikely to actually hit that point. But if you get there, you can do like a random perturbation, right? If I jump around a little bit, I might wind up here, and then I walk in this direction, and I start going down towards P1 prime, right? And then I just keep going. Okay, it's fine, right? But maybe the minimum I wanted to find was going down towards P2 prime, and I went the wrong way, right? So the part of the issue is that there are these different decision points, and you don't know which way to go, and that's kind of one of the big challenges with if you have a saddle point. So one thing, as we'll see, when we're running gradient descent on data, we're trying to optimize something. These functions the blue functions we're creating are going to be derived somehow by looking at data, and it's going to be the sum, right? This example I gave, it's the sum of a bunch of things, and so I can randomly pick a subset of those things to evaluate. And depending on what subset I pick, I might go one direction or the other. I can kind of get out of these things fairly easily with stochastic gradient descent, as we'll see. And an inflection point, that really won't be a problem, but for a saddle point, I might go the wrong way. And that becomes one of the there's like an active research area of what to do about saddle points, right? And it's because you could make the wrong decision instead. Yeah. So hopefully that helps. Sometimes they call the inflection point a saddle point, and okay, that can make a big difference in this course. Well, not really, because we're very seldomly we're not really going to be using one-dimensional functions anymore. Okay. Sure. So okay, good. So now that we've got all this these nonsense points out of the way, we can talk about most points. Most alpha in RD are these regular points. Okay, and you almost always assume you're at one of these regular points and don't worry about it. You often want to say, design a function so there are no saddle points, right? Or if there are saddle points, I can characterize them and I have a strategy if I'm at the saddle point. Okay, and a regular point is is such that let's see, there exist P and P prime in the local neighborhood. So f of P is greater than f of alpha, and f of alpha is greater than f of P prime, and alpha is not a saddle point. Okay, so I kind of need to define, the other real reason I need to define saddle point is because I want to define what a regular point is, and we're usually going to assume we're at a regular point, and it's easier to say, well, it satisfies this property where there are some points above, some points below, but it's not one of these saddle points. Okay, so again, in this local neighborhood, right, this is R2. I've got my point alpha, and then there are going to be some points P and some points P prime, and there's going to be some kind of something going on here where, let me get this straight. So the points P prime are all going to be smaller, and the points P are all going to be larger. Okay, and then ultimately in our gradient descent algorithm, we're going to move in this direction towards the smaller points. Okay, we'll see precisely how to do that. Okay, but most points on a function, on a continuous function, is the one we're going to work with. Almost all of them are going to be these regular points, where there's some points higher, some points lower, right? And so the inflection point in this case, as I defined it, is going to be a regular point. There is a right direction to move. Okay. So we can draw these functions also for, this is a regular point. So I can do this for minimum, too many, I have trouble writing when there's so many M's and N's. Minim, for this minimum point. Well, the minimum point, then all the points are going to be larger. So everything is going to be green. Okay. And if I have, you can have also a maximum point. Maximum where all the points are going to be smaller, right? Everything in this local neighborhood, right? This local neighborhood, again, does not need to be defined by a Euclidean ball, but it doesn't matter really how you define it, so you might as well do a Euclidean ball. That's the simplest thing. Okay, and our goal is to find these minimum functions. Did I do this in the right way? FP is going to be smaller. Yeah. Right. So if once you shift, if I shift this alpha, right? So if I'm at this regular point, right, and I shift alpha to over here, alpha prime, what's going to happen is that I'm going to kind of shift this boundary towards, and everything, more and more stuff in the old local neighborhood is going to look green. So that's why I'm moving in the direction of the pink points, but eventually you get to the minimum and everything is green, because you leave everything behind you as green. And when you're at that point, you don't know where to go. This is kind of like, think of this like this one like this, and this one right here. This is the right way to think about these functions. Okay. And a saddle point, as I've defined it, you can't really draw it in just these one-dimensional pictures. Okay. Okay, good. So this is kind of the basic most of the geometric intuition you need about functions, except the next thing we can also define geometrically. So convex functions. Okay, let's define these, and then we'll move on to gradients and see the calculus view of some of these things. Okay, so a convex function is going to be a super important class of functions. For up until 10 years ago, basically all of machine learning was figuring out how to formulate models so that they gave rise to convex functions, because convex functions, we know how gradient descent works with them super well. Right now, with deep learning and random forest, that's all thrown out the window. But convex functions are still really important to understand. Okay. Okay. So I'm gonna draw a picture here, and this one I can draw in for a simple one-dimensional function, but it will hold more generally. So this is again alpha in RD. This is y. And so convex function is going to look, this one's happens to be convex. And I need to think of a useful way to think of a parameterization of a line. Okay, so I'm going to have 2 points, P and Q. Okay, and I want to think of this line in between them. I want to write kind of this neat way of writing these lines. These points could be generally in RD or R. It's going to be RD plus 1 will be. Okay, I'm going to think of writing all the points on this line. Okay, and I want to write, so this line PQ, and even it can extend off to infinity if I want to. Okay, so this line will be defined as LPQ is going to be a subset of RD, defined as the points X, which are going to be for some lambda P plus 1 minus lambda Q for lambda in the space of real numbers. Okay. Okay, so let's look at some examples. So then I can specify, say, a particular point X is going to be LPQ for some value lambda. Okay, for instance, if lambda equals to 0, what's going to happen? Then LPQ of 0 is going to be exactly Q, because I'm multiplying P by 0. And so again, P and Q are points in high dimensional space, or they're vectors. Lambda and 1 minus lambda, these are scalars. So I'm scaling all the points. So that means when lambda is 0, I multiply the P vector by 0. And 1 minus lambda just becomes 1. So I just recover Q. If I do LPQ of 1, I'm going to get P by a similar argument. If LPQ equals 1/2, I'm going to get P plus Q divided by 2. That's going to be this point here. This is LPQ 1/2. It's the midway between the 2 points. Basically multiplying them each by 1/2, right? If LPQ is equal to -1, okay, I'm going to get something up here. It's going to be extended. The distance from P to Q, I'm going to go that again away from Q. And if L and LPQ, that's right on this side, LPQ, let's say 2, then it's going to be over here. This is 2, this is -1. And I basically parameterized. So I have this is 1, 1/2, 0. I've kind of have this line parameterized by this kind of this linear combination of P and Q. This is another way of defining the span of points in high dimensions. We talked about span in linear algebra before. Okay, so this is a way of defining a line. And we're particularly interested, so in this region in here, this line segment, we'll say LPQ is going to be, so the line segment for Q between 0 and 1, right? That's just going to be these values in between P and Q. Okay. Okay, so what's that have to do with convex functions? This describes kind of the convex combination. This is known as the convex combination of P and Q, which gives me the line segment. If I hit a third point and I could have some way to, some values between there, this is one way to define a triangle. All the points inside were two simplex and so forth. There's a lot of cool geometry, and computational topology is all built on these sort of ideas. Okay. Okay, I'm just digressing a little bit here. Okay, so a convex function, I now need to think about this with respect to 2 points, P and Q here. Well, actually, I want to think of P as being here and Q as being up here. No, I want them to be in RD. Okay. Okay, good. So, I'm going to take these 2 points and I'm going to lift them up. Onto this function, right? So this is a point P, f of P. This is an RD plus 1. This is Q, f of Q, right? This is a point in RD plus 1. Okay, and I want to think about this line segment in between the two. And it's going to be F is convex if basically L, P, Q, or technically P, F of P, Q, F of Q, if this line segment is above F. Okay, that means that, right, it's always above it in this sense. Okay, and we can define this. So typically this is written for all PQ in RD, for all values lambda in 0, 1. Okay, then I'm going to have F of lambda P plus 1 minus lambda Q. So this is the function values for in here, for the function values in here. And I'll write this over again on the next page because it's getting scrunched, but I want it to be next to the picture first. That lambda F of P plus 1 minus lambda F of Q. Okay, I need to write this over the next page. Yeah, I'll write this, the function under the convex definition. Yeah, so I will, I'm going to redraw this picture, but this equation, I'm going to rewrite this and redraw the picture in the next slide. But now while it's all together, I want that for every, if I look at, I have this pink highlighted region between P and Q on the x-axis, right? And for each one of these points, when I evaluate the function, right, for each one of these points, when I evaluate the function value, it's below the line segment between them in the D plus 1 dimensional space. Okay, so I'm going to rewrite this on the next page and redraw this picture. So for all, let's just start out by saying F is RD to R is convex if for all PQ in RD and all lambda in real numbers between 0 and 1, then I'm going to have that f of lambda p plus 1 minus lambda q. So if I evaluate that point, that's any point on that line, then this is going to be less than or equal to lambda f of p plus 1 minus lambda f of q. Okay, so let's draw this picture over again now that I have all of this stuff. This is going to be RD. This is going to be this R value. I'm going to have a function. This is f. I'm going to have 2 points, P. I'm going to have Q, picking any point. I'm interested in this region in between them, right? The region in between them, that's going to be this here. So that's all the points on that line segment in d dimensions in between P and Q. Okay? And now I'm going to compare this to, right? So I'm going to lift this up to these function values. This is going to be P f of P, and this is going to be Q f of Q. These are in D plus 1 dimensional points. Okay, and so these are these points here, and this is f of Q, this is f of P. Okay, and so I'm going to match it. I'm matching its x-coordinate already by this bottom part. And so I want to compare that to this line in between them. Right? This line in between them is any linear combination of these d plus 1 dimensional points. This always lies above the function. Right? It's always going to be greater. Right? Greater or equal then. It'll be equal on the endpoints. A straight line, a linear function is convex, right? So it could be all equal, but most convex functions are ones that have a minimum like this. Okay. Okay, so does this make sense? This definition of convex functions. This is, I like to define things geometrically, but this is the standard way to define a kind of a convex function in this way. And these are going to be really important. We're going to, for basically this class until roughly the last lecture, we're going to be trying to make things convex. Okay. Okay, so let me talk about some properties of convex functions. Things that are really cool. Okay, so the first kind of, if I have a function f of alpha, which equal to h of alpha, which is f of alpha plus g of alpha, and f and g are convex, then h is going to be convex. Okay, so if I have two convex functions and I add them up, then h is going to be convex. This is super important because we're actually going to find all of our functions as sums of contributions from each of the data points we have, or each of the training data points. There's going to be some cost association with those, and we're going to add them up. And if each of those are convex, then the sum has to be convex, right? This is super important. We can also say that f of alpha, if this is equal to the max of f of alpha, g of alpha, then F and G convex imply H is going to be convex. Okay, yeah, so if we take the max of two convex functions, that's also going to be convex, right? So we can also use a max operator. This is less commonly used, but yeah, but if we'll see like a hinge loss that's going to do something like this, that'll imply the hinge loss is going to be convex, for instance. Okay, probably the single most important property of a convex function, right, is that any local minimum of convex F is also a global minimum. Okay, so if I have a convex function and I found a local minimum, right? I found a spot where in every direction I go, I'm increasing, right? It's increasing in every direction I go. I know it's the global minimum. Okay, there's basically, it means for a convex function, there's only going to be a single minimum, and it's going to be the global minimum. Okay, and if I have a strictly convex function, we'll define what strictly convex means later. Then there's going to be a single minimum. It's going to be the global minimum. Okay, I can have a convex function that is going to have multiple minimums still. So remember this function here where it's flat in the middle. This function is convex. This is convex, but it has it has multiple global minimum. But any local minimum, any point along there is going to be a local minimum and is also going to be a global minimum. It's still a convex function, but if it's strictly, so what's called strictly convex, which we'll define soonish, then it's going to have a single point, which is the global minimum, and it'll have other nice properties. We'll come back to these strictly convex functions. Okay, and other properties that have to do with gradient descent. Okay, but this means that if we have a convex function, our f is convex, and then we can basically keep walking in the direction that the function goes down, and we'll eventually reach a point where we can't move anymore. That's a local minimum, and that's also going to be the global minimum. That is the optimal solution, right? So if we have a convex function, we walk in the direction the function goes down, we will attain the optimal solution, right? Which sounds is as awesome as it sounds, right? This is the foundation for most of machine learning for a long time. That's how everything kind of worked. Okay. Great. Okay. All right, so I've been going a little bit slower than I wanted to, but we're going to define gradients. And I'll probably review some of this at the beginning of next lecture. Okay, so the first thing we need to define is directional derivatives. Okay, a directional derivative of a function f from Rd to R is going to be using a direction, which I mean as a vector u, also in Rd. U is equal to u1, u2 up to ud. So that, and by direction I mean that I usually means that it's a unit vector. Usually use u if it's a unit vector, and then the directional derivative, which is this nabla. This is called a nabla so it's the name of it. That's how it's referred to in LaTeX. of f of alpha, and I put the sub u there. So if I don't have the sub u, this will be the gradient, but we'll define them through directional derivatives, is going to be defined. So similar way you define so derivative of f of alpha plus h is a scalar value times u minus f of alpha divided by h, right? So as h goes to 0, I'm seeing what is the infinitesimal change in the function value in the direction h, right? That's, but now I'm sorry, in the direction u. So now I'm in d-dimensional space. I want to get back to one-dimensional setting, which is easier to think about. And I can do that by instilling a directional derivative. And I can just worry about the derivative in this one direction. Right, and so we're going to worry about differentiable functions, which are where this is always defined. So if nab f is always defined, then f is going to be differentiable. Okay, we're not always going to deal with differentiable functions or things sub-differentiable where there are a couple of, one or 2 points where it's not defined, but usually it's not too hard to deal with those issues. Okay, so we're going to assume that you can actually define this, that you can take this limit. Okay, and we're going to be interested in directional derivatives where we want u to be from this set E1, E2 up to ED, where EI is going to be a function that looks like this. Okay, where this is in the ith coordinate for EI, right? So it's an all zeros vector except for a 1 in the ith coordinate. And so this is just the coordinate axis. This is, if I just have two vectors in two-dimensional space, it's the x and the y-axis. X is 1, 0, and y is 0, 1, right? But in high dimensions, these are the coordinate axes, right? And then I can define, then I often use for shorthand notation, nabla I is f of alpha equals nabla, where I use this EI as this u direction. Okay, and this turns out this is exactly d alpha I. So the ith coordinate, right? Remember, we have that, I assume that, yeah, so this was alpha. Right, so the alpha is this d-dimensional vector. That's the parameter space I'm taking the derivatives over. And this gives me the kind of the derivative in the ith coordinate. Okay, and so now I can treat the ith coordinate as the variable alpha I and everything else as constants, right? So then I can take derivatives. Okay, and finally I can define the gradient, okay, as nabla f with no subpart here, which is just going to be d of f d alpha 1 times E1 plus d of f d alpha 2 times E2. And I can also just write this because each of the, now I have a scalar value, right? The derivative over one coordinate is a scalar value. I'm multiplying by that a vector, but it's almost all zeros vector. So then I can just write this as this, each one defines a single coordinate, d alpha 1, df, d alpha 2, to df, d alpha d. Okay, so the gradient is just each coordinate-wise derivative and each coordinate put together in a vector. Okay, so nabla f is a function from Rd to Rd. It gives me back a function in Rd. Okay, let's go through and do an example. Okay, so let's start with alpha. I'm going to write as x, y, z in R3. Okay, and my function of x, y, z will 3x squared minus 2y cubed minus 2x e to the z. Okay, where e is the natural constant. Okay, I'm confused. Does d denote the derivative or does d denote the variable? So there. Okay, so I've got two types of d's here. If you look in the book, they're written in slightly different fonts, and I've written them slightly differently here. There is this sort of d where I go back down with the writing, and this is the dimension of the space. Yeah, and I've also got this sort of d. Let me try that one again, where I just go up. This will refer to the differential operator. This one shows up like here, right? This sort of one. Okay, so I'm doing a differential operator. There's usually kind of again, that's d is the common, this one place where d is overloaded. I try not to do it too much. But so it's a differential operator. Alpha is my variable here. Okay, and I can get the gradient by only worrying about one variable at a time, leaving the rest of them fixed. I'll go through an example, hopefully makes it a little bit more clear, where d in this case is 3, so it's not something that's just lying around here. Okay. Okay, so I can write, for instance, df dx. Remember, x is, this is alpha 1, alpha 2, alpha 3 are x, y, z. Okay, so df dx, hopefully you've seen something like that before. That means y and z are constants, right? So df dx should be, it's going to be the first term, it's going to be, let's see, 6x, but x also shows up in the third term. So I'm going to be minus 2e to the z. Okay, df dy, right, it only shows up in the second term. So this should be minus 6y squared. And df dz is going to be, that only shows up in the third term, and this is going to be minus 2x, which are constants, and then the derivative of e to the z is e to the z. So I get that back. Okay, so these are, the sort of derivatives you're going to have to do. You may have to expand polynomials and take a derivative, but most of it is going to be polynomial derivatives once you isolate the variables. Okay, and so that means that nabla f, right, is going to be equal to 6x, the derivative of x, of f, the derivative of f is going to be 2e to the z, comma, again, this is a function, right? This is a function, minus 6y squared, a function to three-dimensional space, 2x e to the z, okay? And then I can evaluate this function. What is e here? E is 2.71, right? It's the natural, it's the base of the natural log, right? It's this thing that if you take e to the z, take the derivative with respect to z, you get back e to the z. It's this very special constant that shows up in the Gaussian, the natural log, and a bunch of other things, like in entropy. Yeah. So if you've, assuming you're just clarifying, but if you have never looked at like the Wikipedia page for the constant e, it's pretty cool. Yeah. Okay. D of f now let's evaluate this. We can evaluate this at a point, right? So let's evaluate this at a point, 3 minus 2, 1. That's a three-dimensional point. We can evaluate the gradient. It's going to give us back a constant three-dimensional vector. And we basically plug this stuff in. X is 3. So the first coordinate is going to be 18 minus 2 times e to the z. Luckily, z is 1. So this is 2e. Y is minus 2. So this is going to be minus 24. And the z coordinate is going to be minus 6 times e. Okay, so there, the gradient is a function from R3 to R3. The input is 3 dimensions, 3 minus 2, 1. The output is 3 dimensions, 18 minus 2e, minus 24, and negative 6e. Right, I could multiply it with the constant, but that's usually leave it as e, I guess. Okay. Okay, good. Right, so this gradient is basically just taking these partial derivatives. What is this telling us? What's the application? Okay, great question. This is great. I'm going to try and draw a function here. In the next lecture, we'll draw functions with Python that can do them in ways that look a little bit nicer. But basically, we're going to have some function f, right? And we're kind of defining this abstractly, right? And think of this as alpha and RD. And I'm going to add some particular spot alpha. And I'd like to know which way to go, right? And so I'd like to go down. I'd like to go the direction that the function is decreasing the most. In one dimensions, this is kind of obvious. In high dimensions where you only have access to a function and maybe you can take its derivative or its gradient, then the gradient tells you that, the direction of steepest descent. So I want to go, this is negative f, the negative of the derivative of f at the value a. Okay, so what this tells us, okay, is that I can recover the directional derivative of f of alpha. I can recover this, it turns out, by nabla the gradient of f at alpha dot with the direction u. Okay, I can get the directional derivative by taking the dot product. U is a unit vector, and so I just want its components along the gradient, which we remember from this definition was just, I took all these individual coordinates, E1, E2, and so forth, and I calculated the derivative of each of those. That's what the gradient is. So I can decompose this direction u along those coordinates, and that's just the dot product. That tells me the directional derivative in that direction. Okay, so then I can ask which direction u is the directional derivative of f at u, the largest. Okay, and remember, u is a unit vector, so we only get to pick a direction, and this is maximized. So when u is actually in the direction of the gradient, right? The answer is when u is equal to this divide, so it has to be normalized. Sorry, shouldn't be a u in there. Okay, so when I take the gradient, which is a vector, and I normalize this vector, that's going to maximize this dot product. A dot product is maximized when I take the dot product with itself over all directions, right? So this maximizes the directional derivative. That means that's the steepest increase. Okay, and so if I want the steepest decrease, I go in the negative direction. This is the steepest descent. Okay, so the negative of the derivative at a function value alpha tells us the direction that the function is decreasing the fastest. If I move in a unit direction or an infinitesimally small step in any direction without controlling the length of that, how fast can I get down? Well, that's what the negative of the gradient tells us. If we want to go up, we want to maximize, I'd go in the direction of the gradient. If I want to minimize, I go in the negative of the direction of the gradient. Right? Right, so this negative sign is important. Okay, I got through everything I wanted to get through. It's a little bit rushed at the end, so I'll probably try and review this a little bit at the start of the next lecture. But kind of, if you have a convex function, right, it means that there's going to be the local minimum. If we can get to it, then we found the global minimum that represents our cost function of a particular model value. And if we can take the derivative of the function, then we can find the direction of the steepest descent. And if we can walk down in that direction, we're eventually going to get to the minimum, which is the global minimum, which is our optimal model, right? So this is kind of how it is. Okay, so let's stop there for now for this lecture. And then next lecture, we'll kind of continue, kind of review, and we can ask questions about these topics, and we'll start talking about the algorithmic applications of this and kind of how well this actually works and what we know based on the description of the function.